I'm Jamie Weaver from Global Epidemiology at Janssen R&D and a DPhil student at University of Oxford. This work is titled Defining the Analytic Space for Valid Outcome Misclassification Correction Using Quantitative Bias Analysis, or QBA. This content relies heavily on the strong support from my collaborator Dream Team that you can see here. Phenotype definition measurement error is the result of discrepancy between the clinical description of a medical condition and its operationalization for identifying cases and observational data. Although measurement error is regularly acknowledged, its impact on information bias in safety and effectiveness causal estimation studies is often speculative and relies on heuristics. QBA methods can correct effect estimates subject to outcome misclassification given the following inputs: an exposure outcome contingency table, like the common 2x2 table, which provides the outcome incidence proportion and effect estimates such as an odds ratio. It also needs the outcome phenotype definition measurement errors derived from a validation study, such as sensitivity and specificity, or positive predictive value and negative predictive value. As a toy example, say a study produces the following 2x2 table with a relative risk of 2, and further, say a validation study samples and confirms as true positives 9 out of 10 target exposures and 8 out of 10 9 out of 10 target exposure cases and 8 out of 10 comparator exposure cases, which gives an exposed PPV of 90% and a comparator PPV of 80%. An intuitive QBA application is to multiply the target and comparator case counts by these error metrics, which simply rearranges the contingency table distribution. Recomputing the relative risk now shows a corrected estimate of 2.25. But a main problem with these types of algebraic table rearrangement equations is that certain input combinations can produce negative corrected event counts, and this invalidates results. Despite awareness, QBA adoption is low and generally understudied in pharmacoepidemiology. The input combinations or scenarios where QBA produces valid or plausible results are not well understood. By valid, I mean where the corrected contingency tables have all non-negative event counts, and by plausible, I mean where the corrected effect estimates don't differ from the uncorrected by many orders of magnitude. We assess the operating characteristics of QBA for outcome misclassification correction across a large set of plausible causal estimation scenarios to report on which scenarios its performance is valid and plausible. So, to do this, we created a large grid space comprised of all combinations of 6 outcome incidence proportions ranging from 1 in 10 to 1 in a million, 6 odds ratios uncorrected for misclassification, 20 outcome sensitivity values ranging from 5 to 100%, 20 specificity values, each conditional on the incidence proportion of the scenario, and this resulted in over 14,000 2x2 tables representing all of these inputs. Here's a visualization of the grid space. The rows represent the input incidence proportions, and the columns represent the input uncorrected odds ratios. Each cell is its own sensitivity by specificity plot for a unique incidence proportion by odds ratio combination. Let's review the plot where the incidence proportion is 10% and the uncorrected odds ratio is 1. In this scenario, we see a range of specificity values on the y-axis from 99 to 100%, and sensitivity on the x-axis ranges from 5 to 100%. With no measurement error, the sensitivity and specificity value each equal 100. We see 100%. We see the null estimate in the upper right. The 3 curves are the contours of the 25th, 50th, and 75th percentile of the corrected estimate distribution across this space. In this scenario, the maximum valid QBA adjustment to the uncorrected estimate is about 20%, where sensitivity is around 5% and specificity is 99%, which is in the lower left. Now, if we vary the input by increasing the uncorrected odds ratio to 4, we get another scenario where we see a narrower range of specificity values on the y-axis from 99.6% to 100%, and the sensitivity on the x-axis still ranges from 5 to 100%. With no measurement error at all, we see the estimate of 4 in the upper right. Again, the 3 curves are the contours for different percentiles of the corrected estimate distribution across this space. In this scenario, the maximum valid QBA adjustment to the uncorrected estimate is greater than 400%, where the sensitivity is around 5% and specificity is 99.6%, which we can see in the lower left. And although mathematically valid, this is a highly implausible result. Next, let's vary the input by decreasing the outcome incidence proportion from 1 in 10 to 1 in 1,000. In this scenario, the range of specificity values on the y-axis is narrower still, now from 99.9% to 100%. With no measurement error, we see the null estimate in the upper right. And again, the three curves are the contours at the different percentiles of the corrected estimate distribution. In this scenario, the maximum valid QBA adjustment to the uncorrected estimate is 16%, where sensitivity is at 5% and specificity is 99.9% in the lower left. The main finding is that very tiny specificity changes have considerable impact on correction, but sensitivity has little impact at all. As we move down and right across the grid, we increase the uncorrected odds ratio and decrease the incidence proportion input. We see a similar pattern. The range of specificity values needed for valid and plausible results gets progressively smaller, meaning that very small and precise specificity changes considerably inflates the magnitude of the correction. The specificity ranges from 90 to 100% in the upper leftmost panel to 99.999% to 100% in the lower rightmost panel. The sensitivity progressively exerts less impact as the uncorrected OR increases and the incidence proportion decreases. To summarize, we identified the analytic space where QBA for outcome misclassification correction is implausible or invalid, and much of this space corresponds to common pharmacoepidemiology comparative effect estimation scenarios. Correction with imprecise specificity is problematic because small specificity changes can make implausibly large effect estimate adjustments, and the impact of sensitivity on correction is limited to where the incidence proportion is less than 1 in 100. The implications for these findings are pretty widespread. A relevant example concerns COVID-19 vaccine safety research, where we've learned from recent Odyssey network studies that many important COVID adverse events of special interest, including thrombosis with thrombocytopenia, are rare, and that their very heterogeneous incidence across diverse data sources could be attributable, at least in part, from variable measurement error across sources. There are a couple possible paths forward, and these include the continued development and broader adoption of more precise measurement error estimation methods, such as large-scale validation using probabilistic reference standard that we know as phi-valuator, or the development of alternative methods for measurement error correction and causal effect estimation, such as the proposed prior knowledge guided integrated likelihood estimation method for information bias reduction. Thank you all for your attention, and my apologies that I can't be with you in person today, but please feel free to contact me with questions. Thank you.